Well, it's December 6th, and I'm going to talk about muons today. Well, muons are charged leptons, very much like the electrons. Now, electrons are the particles that whiz around the outside of atoms, and they're everywhere. Without electrons, we wouldn't be able to power anything electronic. Electrons are actually fairly boring as particles go, but muons are a bit more exciting. Now, when they were first discovered, the famous scientist Rabi exclaimed, "Who ordered that?" It was a particle that had exactly the same properties as the electron, but was heavier. That was the only difference between them. The muon is about 250 times heavier than the electron. Nobody seems to know why. There's no reason why the muon would have that particular mass. We do know that we need at least 3 generations of matter to get the CP mixing, which I mentioned on December 3rd, but beyond that there's no real reason to have these additional particles. They're just there. Now, the cool thing about the muon is it lives for such a long time. It lives for about 2 millionths of a second, which doesn't sound like a lot when you compare it to things like, a human lifespan or the length of a day, or even how long you have to wait to get popcorn in the microwave. But on the scale of particle physics, that's huge. With 2 microseconds, you can go the whole length of a detector. And that makes muons very attractive to us experimentalists. If we see a muon, then we want to make sure we save that event, store it to disk, and analyse it, because there's probably something very interesting happening. And the signature of a muon going all the way to the outside of the detector, it's a very clean signature for us. Now, one of the cool things about muons is they don't interact much with matter, which is really nice, because they get produced in the upper atmosphere. We have cosmic rays coming in. We don't genuinely know where the cosmic rays come from. It's one of the big mysteries of astrophysics and cosmology, the sources of all these things. Anyway, they come in, they hit the upper atmosphere, and they produce a shower of particles. And generally, the only particles that make it all the way down to sea level where they can be detected are the muons. And so you may have seen some cosmic ray detectors, and what they are muon detectors. It's just a spark chamber, a muon comes down, it generates pairs of particles, and you see that as a spark. And muons coming from outer space can actually hit our DNA, and that can lead to mutations. So in a sense, the muon has actually helped evolution along the way by giving us the random mutations that then get selected. So the muon is a really cool particle. It is the first example we saw of the second generation of matter. The similarity between electrons, muons, and the third charged lepton called the tau is known as lepton universality. And it's one of the principles of modern physics that these 3 particles act in exactly the same way, apart from mass effects. They have different masses, and that leads to slightly different things like different decay products and different lifetimes, but otherwise they're exactly the same. And so far, there really hasn't been any strong evidence of a violation of lepton universality. There is one which I'll come to in a later video, and that's very exciting in itself. So we have these charged leptons, the electron, muon, tau, exactly the same apart from their masses, and the muon is one of the most beautiful and useful and cleanest particles we have in particle physics.